Hello. This is the recording of a statistics course I taught in spring 2025. It's about Bayesian statistics and specifically using Bayesian statistics with the brms package. So let me introduce myself. I am Benjamin. I work at the iDiv. This is the German Center for Integrative Biodiversity Research located in Leipzig. I am both a researcher and a statistical consultant. Originally, I started as a mathematician. I did my PhD in applied mathematics more than 10 years ago, but nowadays I would definitely call myself a quantitative ecologist. To me, this means I am using mathematical models to describe aspects of ecosystems, but also statistical models to gather evidence from empirical data. And specifically, what I'm doing most of the time is I combine these two approaches, which means I'm using statistical methods for process-based models, so simulation models. Think of population dynamics, time series, and so on, to estimate species interactions or feeding rates, and so on. This course is quite new. I have been teaching Bayesian statistics for a couple of years now, but I started with using STAN. Only a few years ago, I started using the brms package, and this year I decided to invest some time to polish up the course and bring it in a classical lecture and practical format. When redesigning the course, I thought of who is going to attend this course, and I think this course is well suited for 3 groups of people. Well, first of all, I hope you all have been using R before, because we will be relying heavily on coding the models in R. And then these 3 groups of people are maybe the first one, you just have a little bit of stats experience. So I try to keep this course to also accommodate people with just a bit of statistical experience. The second one is you already are a bit more experienced in statistics, but maybe not in Bayesian statistics, and you want to learn Bayesian stats. And the third group is you already have been using Bayesian statistics, for instance, with JAX or with STAN, but you are unfamiliar with the brms package yet. What I hope that we will achieve during this course are the following things. First of all, to my experience, often statistics is performed in a way that you think of a statistical test, and then you think of, okay, what kind of questions can I answer with a statistical test? I want you to think the other way around. You start with a research question and you have some data, and then you should think about what kind of modeling can I perform on this data to answer my question. So think in terms of your question and the models, and not the other way around. We will go through classical groups of models, for instance, linear models, ANOVA, generalized linear models, and so on. So I think this course is useful for you, even if after this course you do not want to use Bayesian statistics and you want to stick to, for instance, LME4, frequentist statistics, and so on. However, I must say Bayesian statistics is becoming more and more popular. You will encounter papers where people have been using Bayesian statistics to answer their research questions, and the basic knowledge of this methodology is required to kind of critically assess the papers and these findings. We will use the very versatile brms package. I think it's perfectly suited for an introduction, because much of the syntax and the code you will know from classical LM or LM4 coding. And I will focus on interpreting the results of these models and doing statistical inference for them, meaning that, doing statistical inference to answer your specific research question. And I hope at the end of this course, you will be able to analyze your own data sets. This course is 8 parts. Each part is a lecture and also a practical. There are also small exercises that you can do yourself, but the solutions and all the material is in the GitHub folder. So we will first, in this lecture, start with a general introduction to statistical modeling. So no Bayesian statistics yet. This will start only in the second and third lecture. And afterwards, we will go through kind of classical groups or classes of models, linear models, generalized linear models, and also mixed effects models. The 7th lecture is dedicated to Stan. So this is a programming language which BRMS is based on. Although BRMS is quite versatile and you can fit a lot of different models with it, maybe at some times either your model or your data set is too complex to analyze it with BRMS. In this case, you have to rely on coding the statistical model yourself. And here we will use Stan. That's the kind of basis or the programming language which BRMS is based on. So in this lecture, I will start with a general review of probability distributions and statistical modeling, with a specific focus on the likelihood function, because we will need this in the next session for Bayesian statistics as well. So let's start with random variables and their probability distributions. So this is a kind of practical example. Sometimes these examples are from actual data. Sometimes I made them up myself, and they will all be kind of mostly be ecology related. So here, let's think of, we have some habitat with a deer population with known size. So this population has 10 individuals. And our question is, how many of these individuals will survive the winter? We don't know this quantity yet, but we can model it, or we can describe it as a random variable. This random variable has some properties. First of all, it is discrete. This means it can only have integer values like 0, 1, or 2, right? So an individual cannot be 50% alive or dead. So it's either alive or it's not. Second, this random variable is bounded between 0 and 10, because we assume there is no kind of reproduction over winter, and the population is 10. So the population after the winter can only be between 0 and 10. And then we have an additional information. We know the average survival probability. So think of, maybe you have measured that in previous years, or you have several habitats where you kind of know the average survival rate. And then we can say, or we can model this random variable as binomially distributed. On the next slide, I will show what this actually means. But here the terminology is, we have a random variable which is distributed as a binomial variable with known parameters. So each distribution has at least a parameter. Here we have 2, and they are known. This is the size of the population and the average survival rate. Distribution is defined by a function. And with this function, we can calculate the probability of each outcome. I actually want to kind of keep this course as much math-free as possible. So here I just wrote down the equation for illustration. We will not be wrangling equations much here at all. So it's more designed as a, with a more practical focus. But we know, okay, there's some mathematical function that can calculate the probability of each outcome, by this formula. If we know the parameters of these distributions, and here we know the parameters, it's the size 10 and the survival rate is 0.6. So you do not need to know this equation by heart. You can just use R to calculate probabilities, for instance, with a binom function, which calculates probabilities of single outcomes. So you can calculate the probability of, for instance, what is the probability of 4 individuals surviving the winter, and then you will get some answer which is 0.1.1 something. You can also kind of do simulations with this, right? If you know the size and you know the average probability or the average survival rate, you can draw samples, so random samples from this distribution. You can think of you simulating the outcome, how many individuals survive, and then you will get one value which is like between 0 and 10. And if you repeat this often and often and often, you will get an empirical distribution which will resemble this, theoretical distribution here, which is given by the formula. There are some properties of these discrete distributions. And here it is that all the probabilities always sum up to 1 or to 100%, right? Because we are 100% sure that the outcome is either 0 or 1 or 2 or 3 and so on, or 10. There are other properties of this distribution. For instance, we can calculate the mean. Here, the mean is given by the size times the average survival rate. So the average outcome, if the experiment, this field experiment, is repeated often, is 6. And this is also called an event. So you can calculate probabilities of events. So here the event is 6 individuals survive the winter, and here you get some probability. Events can be more. An event can also be 6 or more individuals survive the winter, and you can calculate the probability by just summing up these individual probabilities of 6, 7, 8, 9, and 10. Or you can calculate the probability of an interval. Here it is that at least 4, but maximum 8 individuals survive the winter. And here we would be pretty certain, we would be almost 90% certain that the number of surviving individuals is between 4 and 8. So this was a classical example of a discrete random variable. And for discrete random variable, we have discrete probability distributions. Let's move on to the next class of distribution. And this is a continuous distribution. Here, the random variable is not discrete like 1, 2, 3, 4, 5, but it can take any number. Here in this case, okay, I'm measuring individual body mass of an adult deer individual. This can take any value. Well, it must be positive in this case because body mass is a positive number, but think of log body mass, right? So this could take any number. So the log of something can also become negative. So this is a example for continuous random variable. Because it is not limited to just integer numbers. Here in this case, I assume that this random variable comes from a normal distribution. In this case, a normal distribution is defined by 2 parameters. One is the mean, the average body mass, for instance, let's say 100 kilogram, and also the standard deviation. This means how much spread or variation is in the observed body masses. Sometimes I just make up numbers here for just giving you some experiments. The numbers not necessarily all come from real data sets. If you think biologically some values don't make any sense, this is just because sometimes I just made up these numbers. But in the coding part, I usually use actual ecological data sets. Okay, yeah, assume that this random variable comes from a normal distribution. Again, this is our random variable here. And here the normal distribution says 2 parameters. Why do I think that this comes from a normal distribution? Well, mathematically, you can show if you kind of add up a lot of stuff, right? For instance, here, the body size is kind of like the cumulative of how much the individual grew for instance, each week. And this adds up and adds up and adds up. And mathematically, whenever you have some process where something random, it doesn't matter from which distribution it comes, but as soon as you start adding things up with a number that is large enough, then things will become normally distributed. This is why very often we are working with a normal distribution here. And here we have the density function of the normal distribution. So we say a variable is normally distributed if it is defined by this quite complicated function here. It's not important that you kind of memorize this. Again, we can use code to calculate this. But this now is a bit different from the discrete case. So this is the classical bell-shaped curve, or also called Gaussian curve, named after the German mathematician Gauss. But how can we calculate probabilities here? This is a bit different. Because this function at any kind of given outcome here, for instance, at 95 kilogram, this function does not calculate or give you the probability that an individual that you choose randomly will be 95 kilogram. That's the weird thing about continuous distributions. The probability of an exact value is always 0. We will see on the next slide how we will calculate this, but you can think of it like this way. If you have a scale that weighs the individual, and you will put some random individual on the scale, and the scale has like 6 digits, right? The probability that it will be exactly 95.0000 kilogram is vanishingly small. So for a continuous random variable, mathematically speaking, the probability of hitting a value exactly is always equal to 0. However, we can assign probabilities to intervals. So first, the property here is that the probabilities integrate to 1. In the discrete case, the probability summed up to 1, but here they integrate to 1, which means that the area under the curve, this is what is defined by an integral, the area under the curve here is equal to 1. And then with this area, we can calculate probabilities. For instance, here, what is the probability of that an individual is less than 110 kilograms? And the probability is given by the area under the curve, or mathematically speaking, by the integral with an up to the upper boundary of 110. And again, you can also use just R code to calculate this. Here, the P norm function, P norm for the normal distribution of 110 for a distribution with mean 100 and a standard deviation of 10, gives you the probability of, let's say, 48% here in this case. The same if you want to use this for true intervals, which have an upper and a lower boundary. So the probability of observing an individual between 90 and 110 kilogram, that's the area under the curve between these boundaries. And mathematically, you can calculate this by having the area under the curve up to 110 minus the area under the curve up to 90. And what remains is the area in this interval, and this is the probability here. Okay, these were just two basic examples for distributions, a discrete one and a continuous one. We say a random variable has a distribution when we know some function that calculates probabilities. In the discrete variable, or in the discrete case, this is simple. The function assigns a probability to each outcome, right? So the outcome here is 0, 1, 2, 3, and so on. And each of them gets assigned a probability. In a continuous case, we have a probability density function that assigns not a probability, but some density to every single value. And we can use this to calculate probabilities by the area under the curve or by the integral. We will learn a couple of more distributions in the remainder of this course, where we always have to ask ourselves, okay, I'm observing some outcome of my experiments. How do I think, what kind of distribution does this outcome follow? So I'm not going through all the possible distributions here because this would be quite boring. I think we will see in the remainder of this course for every specific example. Whenever we learn a new distribution, I will try to explain it a bit more. Okay, I would continue with the statistical modeling part. Why do we need statistical models? Well, the answer is quite simple. I would say nature is really complex and we need to simplify this. And we do this by using models, not necessarily statistical models, but mathematical models in general, which are always an abstraction from nature. I like to explain this with this kind of classical artwork here from Albrecht Dürer, who is a Renaissance artist, and he nicely depicts some technical progress happening at this time. And yeah, so these two scientists, I would say here, are building a model. And they're building a model of something they observe, right? So they observe some guitar, and they want to produce a model of this, which will have a specific purpose. Their purpose is they want to show a picture of the guitar, which they might be able to show other people to say, okay, here, this is how a guitar looks like. But the purpose is very limited, right? So with a picture, they won't be able to tell other people how the guitar sounds like. So they're very specific to the purpose they are pursuing. Yeah, and they have like this little technique here where they kind of draw a line to get the perspective right, and then they will have a nice drawing of the guitar, which is a replication in 2 dimensions with a kind of realistic perspective. And we want to do something similar, right? So we want to model, for instance, patterns we observe in nature, for instance, trends or differences. But we not only want to model them, right? We not want to just draw this association or this trend. in science, it's needed that we make quantitative statements about them. It's not enough to say, I observe some difference between these kind of groups or whatever. I also have to make a quantitative statement about it to communicate how certain I am about this difference. And in this way, we can quantify things, and models are necessary to make sense out of your potentially very complicated data set. I think of models often in terms of prediction and inference, which are two different directions. If you say, okay, I observe something in nature, or I have some data about something in nature, and I want to model this, I have to ask myself, does my model describe the data well? And this is the direction of prediction, right? I'm predicting from the model something, I'm predicting some data from the model, and I want to make sure that the predictions are in line with the actual observed data. This is associated with two kind of techniques. The first is model fitting, estimating model parameters. And the other one is model selection. So if we have different model candidates, we compare their predictions and see which of these models predicts the observed data better. Then there's this other direction, and this goes more into the I want to make quantitative statements about my hypothesis, and this is called statistical inference. So if I have some model, for instance, linear regression, very simple, I want the data to inform my model, right? To get, for instance, the effect size, and this will, so the data will inform my model. And this is important to keep in mind, that whenever we are doing statistical inference, is that we're using the data to inform the model, right? So we are learning about, in the first place, we are learning something about our model, not about the data per se, but the flow of information is from the data to the model. Yeah, so this is kind of very abstract here, right? So here we have our little sandcastle, but what we are actually modeling usually looks different. So I now want to formally introduce the parts of a statistical model. And usually we have a single response variable, and we want to model this with respect to some predictors. So we want to learn how this response variable is associated with at least one of the predictors. I mean, there's also models without any predictor, but this is a very special case. Usually you have at least one predictor, and you want to learn about the association between the predictor, so some environmental covariate, for instance, and your response variable. However, the data we have usually is noisy because lots of processes generate the data, and we only have maybe one or two or maybe 5 predictors for which we want to know the association. But there's always some error involved, be it from measurement error, or be it from that we kind of did not observe all the possible predictor variables that are associated with the response. But usually our statistical model, so the predictors alone, will not explain everything in the response variable. Yeah, so our predictors here, they constitute the deterministic part of the model. Deterministic means that once I have fit the model, I have like a function that generates predictions from these predictors here. These predictors themselves can be categorical or continuous, right? So categorical, like if your temperature is warm or cold, or continuous if you, for instance, measured the temperature exactly in degrees Celsius. So this is the deterministic part of the model, and with this you will be able to calculate, for instance, the mean regression line of some association. But you know that the prediction model cannot explain the response perfectly, and this this error or this variation is usually called error or residual, and this is denoted as the stochastic part of the model. And the stochastic part of the model is equally as important as the deterministic part. It usually also has parameters like the deterministic part, right? So for instance, the standard deviation in the classical regression model is an additional parameter which is also estimated in the model fitting process. So both the deterministic part and the stochastic part usually have parameters, and model fitting means that I'm estimating these parameters. Let's go on to a simple example here. So imagine you want to measure some linear relationship between age and body mass, and I want to fit a linear regression here. So I chose sea turtles here because I can be more sure that in this example, this relationship kind of will be monotonous. For instance, the deer population from before, at some age, maybe the kind of increase in body size will get more shallow. But here I chose an example where you can be more sure that the observed data follows a linear trend. And here we are fitting a determinist, or sorry, a classic linear model, which means a regression line. And this regression line already defines the deterministic part of the model. However, usually we think that this is already a simplification, right? Much more processes go into growth than just age as a single predictor variable. But these are unmeasured, and maybe there's also a measurement error and some other sources of variation. So we also have to include the stochastic part in the model. So that means that the actual responses here, the actual observations, are in this case normally distributed around the predicted mean with some standard deviation sigma. And this is a statistical model for linear regression with one predictor, and it comes with 3 parameters. Classically, we have an intercept here. This is A. We have a slope. This is B. So how much does the individual grow per year? But also the standard deviation. This is also a part parameter here of the model. So classically, a linear regression does not only have 2 parameters, but 3, and they can be simultaneously estimated. Don't pay attention to the axis here. I think I centered the predictor here and maybe also the response. So this is not actually age, right? So we have some negative values, but this could be like a mean-centered or standardized age here in this case. Yeah, so this can be rewritten. Sometimes it's easier to understand it in this form, right? So the response here is the sum of my deterministic prediction for every kind of predictor value xi of each data point, plus some error term. And this error term is now assumed to be normally distributed with a zero mean and a standard deviation sigma. And these epsilon terms here, they are called residuals. So they are the difference between predictions and observations. So often people misunderstand this a bit, especially this term here in the middle. People often understand this as the response variable is normally distributed. So here, if you collect all the response variables, or here all the different body sizes here on the y-axis, and you say, okay, they should be normally distributed. But if you look closely, this is not what this equation is saying. This equation says that each response or each observation yi, so I is from 1 to n, is normally distributed with a mean mu I, which is given by the prediction, and some sigma. This is not the same as all the response variables are normally distributed with a joint mean and some standard deviation. No, here in this case, the mean is shifting, right? So each yi has their own mean mu I. And this means that not the collection of all the y's has a joint normal distribution, but the assumption here is not on a normal distribution about the response. It is a classical assumption in linear regression is that the residuals are normally distributed. If you look at this equation again, you see here, if we define it like this, all the epsilons here are assumed to be normally distributed with a zero mean and a standard deviation sigma. So now all of them follow the same distribution. All of them are normally distributed with zero mean and standard deviation sigma. So the assumption here actually is on the residuals. So we assume that they are distributed normally around the kind of shifting prediction, right? So each of these observations has a different expected mean. And the assumption here is on the residuals and not on the actual response. So yeah, this brings me to assumptions. Statistical models usually come with some assumptions. And this is the same in frequentist as in Bayesian statistics. Here, the first assumption is that all the observations are independent. In this case, let's say, yeah, you go to some place where you collect the data, and you make sure that you do not sample an individual twice, right? All of them are independent. Then this assumption is met. If you, for instance, have a small habitat and you go there each year and take some observations, then they might not be completely independent because you have a grouping variable, which is year, which kind of clusters your data. But here in the classical linear regression, you have to make sure that your, see your data as actual independent observations. A second observation, if you want to fit a regression line, you assume that this association actually follows some linear trend and not some other relationship. Then the third assumption, this is the normal distribution of the residuals. Again, it's not an assumption on the raw response values, but an assumption on the residuals. And the last one is, it is already kind of implicated in the third one. This variance here, the sigma here is the same across the whole range of values. So the standard deviation doesn't get like larger or get like smaller across the range of predictor values. So these are classical assumptions of linear models. However, there are kind of workarounds or modeling approaches in case one of these assumptions is not met. For instance, if your observations are not completely independent, you can use mixed effects or hierarchical models for accounting for this. If your trend does not follow a kind of a linear prediction model, there is generalized linear models or even nonlinear models where you can fit curves or other types of associations. If your residuals do not follow a normal distribution, well, it's not a problem. You just have to choose a different statistical model where your residual distribution is not modeled as normal, but modeled as something else. For instance, if your response is discrete, like count data, you can use a distribution for that, for instance, Poisson distribution. And for the last one, if the variance changes, there's also other distributions available that accommodate this feature in the data. To sum up, statistical modeling is a kind of very general principle. It is not per se frequentist or Bayesian. Statistical model is a statistical model. That means it is defined by a deterministic part and a stochastic part, and some model assumptions. And from there, you can go and estimate your parameters or make inference about these models in two different ways. The first one is frequentist, and the other one is Bayesian statistics. But the model or the statistical model itself would be the same. These two methods, they are a bit different in the way they estimate parameters, but especially in the way that they treat uncertainty. And uncertainty is important because you need to somehow communicate how certain you are of your findings. In the frequentist world, this would be done with p-values, and in the Bayesian world, you can, for instance, do this with probabilities. Okay. So, any questions so far? Okay, yes. So the question is, why is it mu of x is a plus b times x and not mu of y is equal to a plus b times x? Let's go back again. Here, x is the predictor value. And I write this as so this is to be read as a function. So mu is a function of x, which means that for every value of x, I can compute the value, right? It is a predictor for the response y, but it is a mathematical function with x as an input, right? For each x, I can put this into this function and calculate the value. So whenever I write some letter of something, I mean, this is a function of, for instance, here, x. All right, so far we defined a statistical model, but we never talked about how to actually determine the parameters of a statistical model, or you can also say how to fit the model to the data. And I start, yeah, maybe with a way of quantifying how do you define a good or bad model fit. So here in this example, so this is a model which is already fitted to the data, right? So this blue line is the best fitting line, whatever this means. I will explain this in a second, for a certain combination of parameter values. So here A, the intercept, this is the value of the response here at x equals 0, and B, that's the slope. How steep is this association here? If we, and here in red, these are all the residuals, right? So the difference between observed and predicted. If I choose the slope a bit more shallow, then this will be a worse fit. The residuals here increase, and if I make it even negative, the residuals increase drastically here. And here, sure, you would say, okay, this is a bad model fit, but how do you actually quantify this? A very, I would say, intuitive way to find the best model fit is, well, you just find the combination of parameters which minimize the residuals here, or the sum of all the residuals. And usually, we do not only want to find parameters that minimize this, the residuals, but which minimize the squared residuals. So here I minimize the sum of all the residuals squared. This has two reasons. First of all, if we wouldn't use the squared, sometimes the model would not be identifiable. But the more practical reason is that squared residuals put more emphasis on kind of on outliers or or values which are far away from the regression line. Yeah, so a very intuitive way, right? So I just want to find a statistic or a parameterization of the model where the errors are small. Okay. But what about other types of models? So for instance, generalized linear models or linear mixed effects models, where the associations is a bit more complicated. And their different measures of model fit might make more sense. And we can actually exploit the properties of the statistical model because we have a distribution, or we have an assumed distribution of the data points, right? So, or of the errors. I will kind of do this with an example. Again, we have the survival rate. And now we always want to ask ourselves, what is the deterministic part of the model and what's the stochastic part? I will do this all the time in the course. I will always kind of focus on what's the deterministic part and the stochastic part. Here, the deterministic part is quite easy. It's just the mean survival rate, right? So there's no predictor involved. I just want to fit the mean survival rate. And the stochastic part now is how is the data distributed around the mean prediction. And here the mean prediction is just the mean survival rate. That's the predictor. And now I have this probability distribution, right? So I assume that the data is distributed like this. And with a probability distribution, I usually have a parameter given, right? So if I know the parameter, if I know the average survival rate, I can calculate the probability of any outcome. So for instance, if I know the average survival rate is 0.6, I can calculate the probability of each outcome, that how many of the 10 individuals survive the winter. Now we use the same thing here in a kind of different way with a different question. Now the parameters are unknown, but the data is given. And this is the case we usually have in statistical modeling, right? So we have the data is already observed. We are not kind of calculating probability of the data because we already observed it. So we know, okay, 6 out of 10 individuals survived. What is the kind of best fitting survival rate for this? So we're using the same model in kind of two different ways. And I would say the one is the reverse way of the other. We talked about probability distributions in the beginning. Now we have the opposite situation. The data is given, but we want to estimate some parameters here. So this way is prediction, right? So if I know the parameter, I can predict different outcomes and also their probability. However, we are in a different situation. Now we have observed some data, and we may want to make some inference on the parameter values, on the, for instance, mean survival rate. So the probability is a function for unknown data, right? So if we know the parameter, if we know the average survival rate, I can calculate the probability of each outcome. So in this case, it is a discrete distribution, but it could also be a continuous distribution. It doesn't matter. We have some formula here. That's the binomial distribution. And for any value of y, I can just calculate this if we know theta. Now, the other way around, we use the same kind of notation here, but now the parameters are known and y is given. And now for any parameter, we can just calculate this value. And then we arrive at something which we call the likelihood function. So here we know, okay, 6 out of 10 individuals survived. So n and y are given here. So this is 10 over 6. And we can compute this for any value of theta. And then we arrive at this curve here. And this means this is some measure of the probability of the observed data for any given for any of these parameter values. And I chose this example here specifically to show you, okay, even if we have a discrete probability distribution, it's discrete for the data, it will generate here in this case a continuous likelihood because the parameter here is continuous. So the likelihood function is some measure of the probability of the data we already observed for some parameter. So how likely would we have observed the data if the survival rate was, for instance, 0.4? Then we get some measure of how likely we would have observed the data if the true survival rate was 0.4. And which parameter would you choose then? Well, you would choose the parameter under which you think that the observed data would have happened as likely as possible. And this is the concept of maximum likelihood estimation. So you have a statistical model and you observe some data. Then you can always define your likelihood function. And it comes from the fact that your statistical model already contains a probability distribution. The statistical model in the stochastic part will always contain some probability distribution of the data. And you can write this probability distribution down. Again, here for the sake of like showing this, I wrote the formula down. We don't need to do this usually because we can just do this in the computer. But by switching what is known and what is given, we can make this a function of the parameter. And we just want to, or we want to choose the parameter under which this likelihood function reaches its maximum value. And this is a point estimate, and which we call maximum likelihood estimate. And this is a method which is much, much more general than least squares. First of all, this least squares estimate, we just, for least squares, we looked at here. Here, the solution mathematically will be the same with maximum likelihood. You can kind of write this down properly and mathematically, and you will arrive at the same solution. But it is much more general. You can use this concept for every statistical model because a statistical model always includes a probability distribution of your observed data with respect to the kind of deterministic model part, and which means you can always, for your statistical model, write down or define your likelihood function. Okay, this was kind of very simple in the sense that we have just one data point, right? So here we had, okay, we have one data point, we have one population where 6 out of 10 individuals survived the winter. So that's kind of just one data point, and we were able to write down the likelihood function for this. But usually you have multiple observations, and in this case, you can also generate a likelihood function. Think of you have like 3 habitat patches, like 3 forests, and you observe for each of the forests how many individuals you had before the winter and how many survived the winter. And then you have these different numbers, 6 out of 10, 14 out of 20, and 8 out of 15. And your question is now, what is the average survival probability here? Here you can, for each of these single observations, you can define your likelihood as we just did it. So you get kind of 3 different likelihood functions. And by multiplying them, you get a joint likelihood function for your whole data set. So you want to find, again, the average survival rate or your value of the average survival rate, which maximizes this joint likelihood function. And this will be your maximum likelihood estimate for the whole data set, which then has multiple observations. So a joint likelihood is always the product of each single data point's likelihood function. In the case of linear regression, here we have now 3 parameters, right? So here we just had 1 parameter, but usually your models will have more than 1 parameter. For instance, here in a linear regression, already 3. So you have to estimate an intercept. So this is A, you have to estimate the slope. This is usually what you're most interested in. But you also have to, in the maximum likelihood framework, you also have to estimate the standard deviation. So these are 3 parameters. And here the likelihood function of all these 3 parameters together, given all your observations, is the multiplication of all these functions here. So the probability density function of the first data point given A, B, and sigma, and so on. So this is now a bit more complicated in the sense that here I just plotted all the values and looked at just extracted the maximum here of for which of these values here the maximum was reached. So this is very simple if you just have 1 parameter. However, if you have more than 1 parameter, this becomes very complicated. Now we want to find 3 values in a 3-dimensional mathematical space, which maximizes this function here. And this is a non-trivial task. So here we are arrived at mathematical optimization, finding the optimal value or the best value for some functions in a multi-dimensional space. And there are several ways to do this. First, if this was possible all the time, our lives would be so much easier. So if there is a possibility to actually derive equations, a mathematical formula for your parameters, this is possible for linear models with Gaussian error distributions. For instance, here there's a formula for this A and B. If you have your model matrix or the matrix or the collection of your values, then you just need a little bit of linear algebra and a little bit of calculus to arrive at these equations here. So you have a closed formula where you just put in your data and out go your parameters. But this is usually not possible for models more complicated than just a simple linear model. Okay, so we forget about that. Next, well, yeah, we can just compute many values in a computer and just look at which one of them produced the best likelihood value. Sounds fine. However, this also becomes computationally completely out of reach for if you have more than just a couple of parameters. Right, so here, if we just have 2 parameters, we can just define a grid. Here for each of these parameters, I will kind of make like, I don't know, intervals of like length of 10. Then I have 10 times 10 values because I have 2 parameters. So I have to compute 100 values and yeah, maybe choose the biggest one of them. But if you have more than 2 parameters, for instance, if you have 10 parameters, then you already would have to compute 10 to the power of 10 values, which already becomes computationally too expensive. So also just brute force is not possible here. However, there's something like numerical optimization. So there's an algorithm that starts at some good guess for the parameters and searches around in this kind of multidimensional space and tries to find the best value. So in each step, it moves a bit closer, and mathematical methods for this have been developed for decades now, and they work quite well and effective. So this is usually what we do in maximum likelihood. This will give you just a point estimate. And the problem is here that the likelihood function is not a probability distribution. It comes from a probability distribution, right? So if the parameter is known and if the data is unknown, it is a probability distribution for the data. However, here we are in a different situation. Here we have the data, but the parameter is unknown, and your likelihood function is not a probability distribution of the parameter. The simple reason for that is that the likelihood function, if you compute the area under the curve here, does not integrate to 1. Doesn't sound like a big issue, but it actually is. Because it is not a probability density function anymore. So you can extract the maximum here, you can compute the maximum, but if you can't, for instance, compute something like quantiles, right? So for instance, here, the interval between 0.4 and 0.8, the value here is completely meaningless. So it does not describe the probability of the parameter being between 0.4 and 0.8. You would have to, this function would need to integrate to 1 over the whole parameter space in order to have like a meaningful value here. So this interval here, or this area here, does not contain any meaning. So we cannot use this to make any statements about probability here. We just can say, okay, this one is the mode, right? So the mode is the location where the maximum is reached, but we can't say anything else about it. However, we could scale this function that it integrates to 1, theoretically. So if we knew this, if we knew the area under the curve here, if we knew this, we could just scale the likelihood function by this value. So we divide the likelihood function by this value and get a new kind of function. In this case, the area here is smaller than 1. And if we divide it by some constant smaller than 1, this whole thing becomes bigger, right? And by scaling it by this factor, we know, okay, the area under this curve is equal to 1, and then we could make probability statements, and we could kind of calculate confidence intervals for the parameter here. We could make all kinds of statistical inference. However, we arrive back at the same problem. We cannot compute the integral here without knowing all the values. So we kind of ran around in a circle. We would have to know this constant c, which is kind of for which we would have to know all these values here to compute the integral, and it's just not practical. It's not possible in any kind of meaningful class of problems or applications. Okay, so this is not practical, but in the next lecture, we will see how we can find a workaround here. So for now, we will stick to maximum likelihood as a way of finding the best possible parameter of your statistical model and some given data. Okay, so statistical modeling is a very broad concept. It's defined by having a likelihood function. The likelihood function is given by your statistical model, which has a deterministic and a stochastic part. The stochastic part connects the deterministic part to the data. Right, so here we have in blue, that's the deterministic part, it's linear regression line. But we have more. We have this, we assume that these residuals here are normally distributed. And this is the stochastic part, so it connects the deterministic part to the data. This is the probability distribution of the data. So we can always write down the formula for the probability distribution. And this always kind of defines our likelihood function. Because if we make this a function of the parameter, of all the parameters, this becomes a likelihood function of the parameters. And we want to find parameters such that the observed data under these parameters are most likely. This is a point estimate only. So we do not get p-values or confidence intervals or anything from this so far. And this means that without additional work, this does not allow probability statements on the parameters. So we can't say, okay, what is the probability of, that my association is actually positive? We just get a value, but we do not get the associated uncertainty, which is required for us to make quantitative statements about our hypotheses. In frequentist statistics, this is kind of shortcutted, or there's a workaround through null hypothesis significance testing. A bit more on this tomorrow. At the end of each lecture, I just have a couple of recommendations on which books or which chapters in each book kind of cover the topic we did in this lecture. But in the last on the last day, I will go through a couple of books and make some suggestions for if you want to learn more about this. Okay, let's meet in 10 minutes, and then I will kind of show you how to work with probability and likelihood in R. Okay, so in this session, we will just learn about a bit of how to calculate the probability, but more important, how to turn this into a likelihood function. And then for purely didactic reasons, I will try to maximize this to get to a maximum likelihood estimate. The likelihood function itself, the concept of the likelihood functions will be super important throughout the whole course. So let's start by, I'm simulating some data. In this case, I will have this deer population again, right? So we will have a couple of, or we have a population of a certain size, and we just count how many of them survive the winter. And I will make up some data now. I will use a data frame format here, where the total number, that's the original population size. So here we have 3 populations which have the size 18, 25, and 20. And the number of survived is also given, which is 9, 10, and 8. So this is the observation, that's the data set. The question is now, what is the average survival probability? And so this already kind of defines our statistical model. So the deterministic part is just mu, so this is always the deterministic part. Here it is just the average survival probability. Let's call this P, or sometimes I also call it a theta. But here let's call it P. So we do not have a predictor, and we just want to fit the mean of the observed data. The model also has a stochastic part. And here we have the binomial distribution, right? So the data will always be, we assume that it follows a normal distribution, because it has, we have the maximum number, which is always given by total, and some average survival probability, which is, yeah, the parameter we are looking for here. So this number of survived, or for each of these 3 data points, the number of survived is assumed to be binomial distributed with a mean of, with the n equals total, and the survival probability P. Right, so this is the parameter we are looking for. That's the only parameter in the model. Yeah, naively, you could say, okay, well, let's just calculate the mean, let's calculate the mean survival rate in a very kind of simple way. For instance, if we just say data survived divided by data total, then we get the kind of the percentage or the ratio of the survived in each habitat, right? So 3 habitats. And also naively, we could also just say, okay, well, we take the mean of these. So I will just copy and paste this, and I will put the mean around this. And we could say, okay, well, this is the mean survival rate. But I wouldn't advise to do this. This is not a statistical model. We lose some information here, but I will talk more about this when we actually talk about generalized linear models. For now, we just want to focus on doing this the proper way, by defining kind of this binomial distribution and so on. But first, let's talk about probability. So if we know the average survival rate, we can calculate the probability of survival. So let's assume we have, we know that there's an average survival rate of just 0.3. So very harsh environmental conditions, only 0.3 out of, 0.3 survive the winter. We have an initial population of 20. So I will code this as X or the age is, oh no, sorry, not age, the outcome is between 0 and 20. And for each of these outcomes, we want to calculate the probability. Then we can do this with a binomial function. So y is equal to a binom of, now here we have x equal x. So for all of these outcomes, we want to calculate the probability. Size, so this is n, this is the population size before winter is 20. And now in this case, we assume we know the initial probability, or sorry, the survival probability, which is 0.3, right? So the data is given. So for each of these data points, sorry, the other way around. The probability is given, so the parameter is given, and we want to calculate the probability of all the possible outcomes. We can plot this nicely with a bar plot. Y tilde x, this should, yeah, give me the probability distribution here. So if I know the probability survival or average survival probability, I can calculate the or the survival rate here. I can calculate the probability of each outcome easily with this binomial function here. The same thing if you would have a higher survival probability, for instance, let's say 0.8. Then we get another distribution here. And again, this is limited by 20 because the population only has 20 individuals. Okay, if we know the parameters, we can calculate the probability of the data. This is probability. Now we turn things around, and we know the observations, we know the data, and from them we want to calculate the parameter. In this case, the parameter is average survival rate. And we can use the same function here. But in this case, not x here is no, x here is the unknown, but now the probability is unknown. So for each of my values p, I want to calculate this function. So this is now a sequence from 0 to 1. So I just define a sequence of survival rate values for which I want to calculate the likelihood. This is just a sequence starting from 0 and going until or going up to 1. And now I can define, like, we can calculate likelihood values. So the likelihood is defined again. Yeah, I can just take the same here. Now the probability here I exchange and put in p. For all of the values I want to calculate the likelihood. And now for x and the size, I have to put in an actual observation. So let's check the first one here. Oh, it's 9 out of 18. So 9 out of 18. And this calculates likelihood for each possible parameter value for these data points. Check again here. Here probability, so this parameter was known, and I calculated this for each kind of possible outcome of the data. Now here the data is completely known, and I compute this for each possible parameter value. So even if we have a discrete probability distribution, the parameter we are looking for is continuous. So the likelihood function also is based on continuous continuous inputs in the x-axis, right? So for each of these possible values for survival rate, I can calculate the likelihood of this first data point. And here in this case, I mean, I think it's fairly obvious that the maximum likelihood here would be 0.5, right? Because 9 out of 18 survived. So the maximum likelihood estimate for this first data point's survival rate is 0.5. However, there are also other data points. For instance, the second one here, let's look this up. Here it's 10 out of 25. Okay. 10 out of 25. And for the next data point, the likelihood function looks a bit different and has a also different mode here, different location where the maximum is reached. Oh, there's a question. Okay. Yes, in the simple case here, we are kind of testing all possible parameter values. And here I defined a sequence of parameter values, 100 values between 0 and 1. And for each of them, I can calculate the likelihood. And then I can choose, or I can find the one of them that produced the maximum value. Here, this is possible because we just have one parameter. This becomes unfeasible if you have 2, 3, or more parameters. This is not a probability distribution, right? A probability distribution must have the property that the area under the curve is equal to 1, which is not the case here. You can check this with a nice little function. It is in the library sfs-misc. And this contains a function which is called integrate.xy. And this function gives you the area under the curve for a given set of, or a vector of parameters that are along this curve. So here, if we put in x values and y values, so the x values are given by p, and the likelihood, or the y values are given by lik. So this is a vector of p is a vector of the x-axis, and likelihood is a vector of the y-axis. And here I can calculate this value. That gives me the integral, or the area under the curve here, which is much smaller than 1. Means we can't use this function here for any statistical inference, right? So we can't use this for calculating, for instance, the probability. So what's the probability that the survival rate is larger than 0.3? We can't compute this from this function here. And this, in the next days, is what we actually want. We want to assign probabilities to hypotheses. Here, for instance, the hypothesis would be the average survival rate is larger than 0.3, and we want to calculate this, the probability associated to this hypothesis. And we can't do this here because the likelihood function itself is not a probability distribution for the parameter. We could turn this into something we can use by dividing this likelihood function by the whole integral. So it's saying, okay, C is equal to this value here. And then we plot P versus likelihood divided by C. You see nothing changed. It looks the same, but the scale here is different. So by knowing the integral here, we can scale this whole thing into something which we can use for calculating probabilities. But usually you do not know this value of this integral. This is only here, again, this is only possible because we just have one parameter and we just can use this nice function to calculate this. If you have more than, let's say, 2 or 3 parameters, this becomes really unfeasible, and we do not have access to this, to this way of calculating the integral. So what do we do? Well, first we can just kind of guess values and try to find the best or try to find a parameter value which maximizes the likelihood function. Yeah, and for the sake of completeness, I will kind of write down the likelihood function for the whole data set. And so the likelihood function for the whole data set is just a product of the single likelihood functions here. So the first data point was 9 out of 18 times, now I can just copy and paste this and exchange some values. The other data point was 10 out of 25, I guess. And then the next one was 8 out of 20. Okay, so this is the likelihood function for the whole data set. And one thing you might already see is that these values here, they become really, really small. Usually these, so these are probabilities of the data, meaning that the values themselves are between 0 and 1. Even if it's not a probability of the parameter itself, it comes from the probability of the data, which means that these values here are between 0 and 1. And what happens if you multiply many values which are between 0 and 1? Well, you will get something very, very small. So if you would continue this and have a data set with like 100 values, each of them being smaller than 1, and we multiply them, we will get something which is really, really small. And at some point, if you have 1,000 data points or more, we might end up with something which reaches the computational accuracy of your computer, which can happen really fast. And therefore, usually you do not use the likelihood function, but the log likelihood function, which makes things easier. So instead of so if I will call this log likelihood now, and I can just put in the log around all of this, right? So I compute the log of all of this. And again, I make a plot. The first thing we observe, I mean, hopefully you can see it here, but the maximum is reached at the same location. It looks a bit different here, but both of these functions, so the likelihood and the log likelihood, both of them have the maximum at the same location. This means we don't have to use the likelihood for maximization. We can also use the log likelihood for maximization. which often makes things computationally a lot easier. We can write this in a different form by using properties of the log here. The problem is here that we multiply all of these very, very small values. However, if we kind of use classical mathematical notation, so the log of the product is the same as the sum of the single log values, then we can turn this here into a sum. So I take the log of the first value and add the log of the second value and add the log of the third value. Then I haven't changed anything. So this is the same as this, just in a different way of calculating this. And here we do not have to multiply all of these small values. We just take the log of something, add the log of something else, and so on. If I plot this again, it's the same, right? And this is usually how things will be computed. You do not use the likelihood value, but you use the log likelihood, and it can be computed in this kind of computer-friendly fashion, such that we do not get any numerical errors there. Okay. Yeah, in this case, I just kind of plotted it against this parameter, and yeah, we can also we can also extract for which of these parameters here the maximum is reached, because we just had one parameter. Usually it's not that simple. And I want to continue with another example, which eventually will have more than one parameter, and we use kind of mathematical optimization to find the best parameter. But don't worry, we don't have to do any math ourselves. We just have to write the likelihood function in a way that we can hand it over to an optimizer function in R, which will kind of iteratively find the best parameter. So the next example is again an example from the lecture. It is the mean body size of a mammal population you want to find. Here we have, again, just one parameter. Oh, no, sorry, we will have two parameters. So let's say we have some data observed. And the body weight of I think it was a deer population. I will just make up some random numbers here. So we have a couple of data points. And what do we want to do? We want to estimate the mean weight. And for this, sure, we could just say we take the arithmetical mean, but we want to do it the proper statistical way here. So we write a statistical model for this. Deterministic part, which I will always call mu, is just that. So we just have one parameter, which is already the kind of mean prediction. And the stochastic part is that, yeah, each observation of weight should be normally distributed around this joint mean mu and some standard deviation sigma. So we just have one joint value here, no predictor involved. And then we can write down our likelihood function. Okay, yeah, so we will again start with a vector of possible values for which we want to calculate the likelihood function. However, note this here, we have now two parameters, right? So if we have a mu and we have a sigma. So first we want to plot the likelihood function for a fixed value of sigma, but the mu will be different values. So we will have 100 kind of possible values for our mean body mass. Sigma, let's keep this fixed for now. Let's say this is 10. And now we can write down the likelihood function. So the likelihood function is let's say for the first data point only, the norm of the first data point. In this case, it's data weight, and this is the first data point. The mean is equal to, in this case, different values of x. So we're testing all of them at once. And the SD, so the standard deviation, is equal to sigma, which here is fixed for now. And again, we can plot the likelihood function versus these parameter values. And so here we directly wrote down the likelihood function. It directly comes here from the stochastic part of the model. Each data point is normally distributed around this parameter mu and some sigma. And here we see for the first data point, the likelihood function of each possible kind of parameter value here between 50 and 150. Okay. Now the likelihood function of the whole data set is the product of all of them. I will quickly write this down. But in the next step, what I want to do is to make this also dependent on the standard deviation, right? So we have two parameters here which we have to estimate, and we want to write a likelihood function which is depending on both of these parameters. So here the likelihood function for all the data points is this times the second data point times the third data point, and so on. Just 5 data points. Again, this is not so smart. We could use the log of this and use the sum. But let's keep it like this for now. And then I can plot this again. And you see already here the values are becoming quite small. Okay, so what I want to do next is I want to write a function where all the data goes in, and also both of the parameters go in, and out comes my log likelihood, or my likelihood. But I will do the log likelihood because it is computationally easier to do this. So I now want to write a function which I will call likelihood. And the function basically looks, or basically does the same as this, but in should go parameters. And the data. And here the likelihood function, or the log likelihood function, is just a normal distribution of all the data. And the mean is my first parameter. And the SD is the second parameter. So it's a function whenever I put in the data and both of my parameters, it will give me all the likelihood values. By specifying log equals true, it will generate the log likelihood values, and it should return the sum of all the log likelihood values. Well, let's call this here log like. So I put in my parameters, I put in all my data, and I get the log likelihood value as a return. And now I will try to perform a mathematical optimization by guessing values. And this is basically what a mathematical optimization routine will do, but in a much smarter way. But to understand how this is going, let's try this ourselves. I will just try to start with some initial values for the parameters. So what is a guess for the data set here? Right, so this is my data set. I want to estimate the mean and the standard deviation. And I will start with just some guess. For instance, let's say the mean is, I guess this is 100, and the standard deviation, maybe this is 10. So we can call this function with both parameters, 110 and standard deviation of 10. And the data is here, data dollar weight. Right, so the data goes in, the parameter guess goes in, and the return is the log likelihood value. Okay. Yeah, these values can become negative, or usually are negative because of the log. Nevertheless, we want to find the best combination of mean and standard deviation that maximize this value. So this value should become larger. And what I'm basically doing now is I'm going into some direction. So I'm increasing the mean a bit and just see if my value changed. Okay, you see, oh, well, the value didn't increase, it decreased a bit. So this is not a good choice. So we're going in the other direction. So instead of 110, I'm going in the other direction, and I say 109. And I see, okay, well, the value increased, so maybe we keep going. Here, the value. Wait, sorry, I was mixed up because of the negative sign. Actually, sorry about that. So from here to here, the value actually increased, right? So it's negative, and so this value here is bigger than this. Sorry about that. So okay, let's keep going here. Okay, but now, so this is bigger than this. So this step here actually didn't make much sense. So we go back to this one. And now the important thing is that we also have to look at the second variable, right? So we can also check, okay, what happens if we change the second variable and see, okay, That's not a good choice because the value decreases. Maybe we go in the other direction. See, okay, it's getting better, and here we can keep going, and so on and so on. So here you try to kind of find iteratively better values. Like you're starting somewhere, you're not kind of coming up with completely new values, but you just move away from this two-dimensional point here. You just move to the next one a bit, and try to go on if your parameter or if your likelihood function increases, or you go in another direction if your likelihood function does not increase. So this is kind of this iterative algorithm what is used for finding these parameters. And we can use the optim function in R to do this automatically. This is the function, it's called optim. And you can put in some function here, just like the function we defined. Some initial guesses for the parameters, and in the background, it will kind of start some iterative process trying to optimize these parameters. Yeah, very good. That's exactly right. With these iterative procedures, you never know when to stop, right? And that's what the algorithm is doing. In each step, the algorithm tests if the changes become if the increase becomes smaller and smaller, because at some point the increases will get very, very small, which means the derivative of the function will become very, very small. Goes up. Yeah. So the algorithm in each step kind of checks if this maximum is reached by saying, okay, here in the peak, the derivative is equal to 0. Right? There's no kind of slope. Like here's a positive slope, here's a negative slope, but in between, in the maximum, there's a 0 slope. And this is actually the mathematical condition for being an optimum, that the derivative is 0, and the algorithm kind of checks that. Yes, we want to put this function, or we want to hand this over to the optim function, that it automatically optimizes this. There's just one little convention which we have to follow. In mathematical optimization, all the algorithms are not written for maximizing stuff, but they are always written to minimize stuff. That's just a convention. Here we want to do maximum likelihood, but the function can only minimize something. Therefore, we change this here and we output the negative. Right, so by flipping the sign, this kind of hump-shaped function becomes a U-shaped function, and wherever the minima of this kind of U-shaped function is located is the same as the maximum of this function. So this is just for mathematical convention. This is called the negative log likelihood function, and we want to use this for optimization. And I hope I get this right. So optim, I say fn, so this is the function, is likelihood. I have to supply an initial guess as parameters par. Here we have 2 parameters, so I have to choose 2 values. Let's say, okay, 110. So 100 is the guess for the mean, and 10 is the guess for the standard deviation. Yeah, and I have to supply the data. And then this function in this case, it's instantaneously, right? If you have a bigger problem, this can take a couple of minutes, but usually in this simple problems with just a couple of data points, it's instantaneously. However, in the background, there was some iterative procedure going on, just the one that we did here. And you see, okay, here it counts 55. It did 55 steps until the algorithm noticed and that the target function couldn't be improved anymore. And these are the estimated parameters. So this is the estimated or the maximum likelihood estimate for the mean of these 5 data points. And this is the maximum likelihood estimate for the standard deviation. Sorry, there's no age involved here. So this was the example where we don't have a predictor, right? So we just have a response. We have 5 observations, and we want, with this maximum likelihood procedure, find what is the mean, the expected mean body size in this population. There was no predictor involved yet. But still, this statistical model here has 2 parameters. It has a mean and a standard deviation. Okay. Yeah, so we didn't make our lives easy, right? So we went through all the steps to solve this maximum likelihood problem. I mean, sure, in practice, you would do this differently. For instance, you can just use LM. And here, the model would be just weight versus 1. So we do not have a predictor, but we just want to estimate the intercept, nothing else. And here the results. Okay, here we just get the intercept, but if we look at the summary, we should get also the standard deviation. So this is the estimate for the intercept and the residual standard error here. This is the sigma, and we estimated both of them here with this other algorithm. Notice here there's a small difference in the parameters of the standard deviation. Because here I think the standard deviation is used by dividing 1 over n minus 1. And the maximum likelihood function did not use that. Yeah, but in general, for bigger data sets, these 2 will give you exactly the same results. Okay, one thing I still want to do with this, I want to plot both the likelihood function versus both the standard deviation and the mean. Right, so previously here, I only plotted the likelihood function for the estimated mean, while the standard deviation was kept fixed, but the likelihood function itself is actually a function of 2 parameters. And I want to plot this now. Yeah, I define a vector mu plot and a vector sigma plot, which are the values which are to be tested. And I will also define a vector sigma or SD plot. Let's say this is from 5 to 15. So that's a reasonable range for both of these parameters. And now I have to do a bit of coding to plot this in kind of a matrix. So the values are generated by the function expand grid. And here I put both of them in. Then I will get kind of this matrix of all the combination of these values. Yeah, so the first one and the second one. Right, so this has length 100, this also has length 100. So this whole data frame has a length of 100 squared, so 1000. Yeah. I will give them names, view and SD. And I will, for each of these combination of values, I will compute the likelihood. So I define a new column here, which is called val.lik, which will contain all my likelihood values. Sorry, I have to initialize this as NA. So this is what I created. So this will contain all the mu values. This will contain all the SD values. And here I will compute now all the likelihood values. And I can use this for plotting. And I'm doing a for loop over all of these values. And for each of them, I will plot, I will calculate the likelihood value. Yeah, that's the function likelihood, which depends on both of the parameters. So for each row, I will extract both of these values, put them in the likelihood function. The likelihood function also has to know the data. And I think that's it. Question is, if we use GLM with normal distribution instead of LM, should we reach the same sigma like with optimum function? I actually don't know. I can try. I guess so. I think if you just use it like this, yeah, I think we have to tell them family. How do we find, is it Gaussian or is it normal? Okay, I don't know why it doesn't give me the standard deviation here. It should include the standard deviation, but I don't know why it doesn't display it here right now. Okay, no, sorry, don't know. But I think it should be the same. Okay. All right, yeah, so we have all these values. So an axis for mu, an axis for sigma. I compute all these values. Now I have to kind of put this in a matrix again, and then we can plot this. So this is a matrix. Yeah, all of these values go in. Dimensions is 100 times 100, and I think then we can finally plot this. Plotting two-dimensional stuff is always a bit tedious, not as easy as with the one-dimensional stuff, so you can have to put all of this in the right matrix form. But this should do it now. Oh, that doesn't look good. Okay, so this is the negative log likelihood, but maybe I can switch this around by doing the exponential. No, okay, something is wrong here, I'm sorry. Okay, I mean, there was must be some stupid error here, so I will just, for this part, show you quickly the solution. So this is how it looks like. There's different values for mu and there's different values for sigma. And the likelihood function itself here has some maximum likelihood estimate here for the values we just computed. And you see that, yeah, it has this classical concentration in the middle, and the likelihood drops if you kind of, yeah, go to the left or to the right and so on. But again, here also in this two-dimensional representation, this so this kind of this curvature here is not a two-dimensional probability function. Here, for now, you just can extract the mean of sorry, the maximum likelihood estimate for the mean and the standard deviation, but you will not get confidence intervals also from this without doing any additional work. Okay, let me just check what we still do here, and the rest will be, as I said, as an exercise, which you can do, but the solution is all included in here. Yeah, we can go one step ahead and now do a kind of proper statistical model where we also have a predictor. And we want to estimate a classical linear regression model here. And here it's the same data, but now we have a predictor, which is age. That's why we have here weight in dependence of age, and we just want to estimate the best relationship here, or the most probable relationship for intercept slope and standard deviation. So what is the statistical model here? So the deterministic part, here we have our mu, which is some parameter a, which is the intercept, plus b times age. And the stochastic part is that weight is normally distributed around some mu, which is depending on age. So mu is a function of age. I could also write mu of age here. But we have some standard deviation sigma. So we have three parameters. It's intercept, it's slope, and it's standard deviation. Yeah, we could easily kind of just fit an LM. Here we would just say weight is depending on age, and data frame is called data. Yeah. And if I print a summary here, yeah, I get some intercept, which is the prediction at age equals 0. So in this case, this would be the age at birth. And this is the effect of age. This means on average, how much does the individual grow each year? If we assume a linear relationship over the whole kind of, over the whole lifespan, which might be unrealistic here, but in this very simple model, this is how we would interpret the parameters. And also we have some standard deviation. It is somewhere here. Where is it? Here, residual standard error. This is how much you expect the actual observations to deviate from the predicted mean. Right, and the predicted mean, with predicted mean, I mean, this is the deterministic model, right? So this is the mean predicted weight depending on age. Okay, again, I want to write the likelihood function for this. I just copy and paste this from here. I hope this doesn't contain the error. What was causing the trouble just a second ago? Okay, we have a function in Go, parameters and data. Data will contain weight and age, and parameters will include all the parameters we need. So we have a normal distribution. The response is data $weight. The mean now is the mean regression line, and it can be computed from the parameters, right? So this is intercept, so first parameter plus second parameter times age. So this is parameter 1. Plus parameters at position 2. Right, so the second parameter should be the intercept times the predictor, which is data $age. Yeah, and the standard deviation here, this should be sigma. And I say log equal true. This, in principle, should be the whole likelihood, right? So it is defined by being a normal distribution of the observed values given some mean prediction, which is depending on the parameters. Sorry, yes, sigma should be parameters at position 3. Right, so for each combination of parameter values, this will produce the likelihood values. There's just one technical detail here. This wouldn't work here because these are all the weights. So this is n observations. This will also produce n values. So we have data age, this is n values. And I think we also have to make this n values of standard deviation here. So we have to replicate this parameter a couple of times. And it's the same as the length of, for instance, data $age. All right, so now we have defined this likelihood, and you could, in principle, do this tedious task of trying to find the best possible values here. So let's start with an intercept of, let's start somewhere close here. Intercept of 8 and a oh no, that's the intercept of 26 and some slope of, let's say, 6 and some standard deviation, whatever. Then you could go on again and try to optimize this, find the best parameter values here and so on. But again, this is a tedious task, especially that we have now 3 parameters here. So again, you could also just use the optim function by saying, okay, I want to optimize the function, which is likelihood. I just have to provide some initial values. And this, yeah, sure. And I have to provide the data. And this works now, okay. Again, we arrive here at the solution, which kind of iteratively, in this 3-dimensional parameter space, try to find the best possible combination of parameters. And you can imagine that if you have more parameters, this becomes even more and more complicated, right? So it has to have the best combination of all parameters together. And this is the maximum likelihood estimate then. Yeah, we can quickly plot this against the data with the AB line. So we can define, we can quickly plot a line here by specifying the intercept and the slope. And this is our maximum likelihood estimate for this small data set here. Okay, so I think we are coming to the end. I wanted to show you that whenever you have a statistical model, which is given by some deterministic part and some stochastic part, you can always define a likelihood function. And the likelihood function is already given by how the data is distributed around the mean prediction. You can always define a likelihood function, but it is now a function of all the parameters, right? So you use this property that the data here is normally distributed around the mean prediction, but you make this here a function of the parameters themselves, right? So the parameters go in here into the mean prediction and into the standard deviation, and this defines the likelihood function. And you can use any method you like to kind of find the best possible value for this likelihood function. Internally in GLM and so on, this is how it is how this computed. Question, please. Okay, not quite. So maybe I'll just write directly to the document. So the first model was mean weight, but we didn't have any predictor X here, right? So there was no X in this model. So the deterministic part was just fitting the mean mu. so it just had one parameter, right? So you could think of it as just an intercept, but there's no predictor involved. And for the second part, yeah, this is for the second part, the deterministic model was then a function of the predictor x, which is a plus b times x. Right, so here, this is a function of x. X is the predictor, or you could also just say h. Mu of h is a plus b times h. Whereas in the other model, it wasn't depending on h at all. We just wanted to fit the mean of the data, and you can think of this as an intercept. So you would just want to fit the intercept, nothing else. So classically, and you can use this. This is a very general framework for almost any kind of statistical model, even if it's like nonlinear whatsoever. As long as you can write down the steps how to compute the likelihood for any given value of the parameters, you can use this to kind of find the best possible parameter, which in this case would be the maximum likelihood estimate. In Bayesian statistics, this is a bit different. However, it still requires this likelihood function. We do not have to know how this likelihood function looks over the whole kind of space of parameter combinations. Right, so here we do not have to know all of these values here. It is computationally completely unfeasible if you have a couple of parameters more. However, you can use this mathematical optimization that starts somewhere here and just finds its way to the best value. Bayesian statistics again is a bit different. It doesn't kind of only find the kind of best value here, but still you need to have the possibility to compute the likelihood function. You have some function that for any given combination of input parameter just gives you the output of the likelihood function, and then you can use this for instance, MCMC sampling in Bayesian statistics. So yeah, I hope I could show you here the importance of the likelihood function, how the likelihood function comes from the statistical model itself. And if you want to, you could try this again with, for instance, a new data set, or where we have a third predictor, right? So you measure, we have different populations at maybe different locations, and locations have different temperatures. So we have an additional environmental predictor, an environmental covariate, and you can try to write this model here, turn this into a likelihood function, and yeah, let the optim function find the best value. However, try to do this for different initial values, right? So you always have to provide initial guess, and try to check this if they all kind of always give you the same solution, right? If you start at different locations in the space, if they all kind of arrive at the same point. This would be a short exercise to, yeah, to go through the steps here again to see, yeah, to check if you understood this correctly. Yeah, from tomorrow on, we will use Bayesian statistics, and we will use the BRMS package. The cool thing is that it comes with lots of handy tools for plotting and plotting predictions. So everything we did up to now was kind of purely didactic. We usually do not have to kind of go through all of these steps to fit the model and also to yeah, try to optimize this. We have tools that do this automatically for us, and which allow us to focus on what is important, and this is making statistical inference.